Now, Hattie, what's on your mind? Don't look at it.
No,
No, you just
I
okay.
just feel gypped, you know, because now I don't just take 44, so I don't find out what the
Room in the
magic
class. It's almost crazy, not that it's crazy, I think, because most of your programs don't require it. But honestly, the courses fit together so nicely that it almost makes sense to just take one out of the day. It's always there as an elective if you need it. You can always come back to take term off, come back to us. Now, this might look terrifying, but it won't. The more you look at it, the more we talk through it, it won't. There's what you want, yeah? That's what you want, right there. You ever going to get it? It's population mean. You're never going to know what it is. Can you get X bar? Yes. You can get it from your sample. Can you get the sampling error? Now, this is a bit of a trick question, because if you look back to that last slide, sampling error is defined to be sigma over root n. So you might say to yourself, you have to know sigma to know what that is. What I'm saying is, that standard error that's right there is going to be the standard deviation in your sample. So that pops back, you've already got the standard error. So in other words, you can get this number from your sample. That'll come up from your sample. So you can get that, you can get that, you can get that, and you can get that. If once you have this, can you multiply it by 2? And subtract that from X bar? And can you multiply it by 2 and add it to X bar? Is this starting to sound somewhat familiar? It sounds like 2 standard deviations is exactly what it is. Essentially what you're doing right here, is you're doing that. Notice how I said, on average, mu will be within a usual range of values. What percent of the time? 95. 95% confidence. 95% confidence. That's it right there. If you go up to 3 standard errors, it's 99.7. You bring it into 1, that's 68%. It's not good enough in the industry's opinion. 95 is standard. So what that means is, yeah, mu is going to be the center of this curve that you can't see. And your X bar might come back off to one side of that. But as soon as you slap wings on it like this, it's going to gobble up mu. That's why you can't say the unemployment rate is 7.6%. You say it's 7.6% plus or minus 3%, or plus or minus 2%, or plus or minus 1. Because your number's probably wrong. But as soon as you stack some percentages up and below that, above and below that, chances are 95% of the time you've got the true value in there somewhere. Now some people say that's not as useful. If you don't know the actual number, it's not as useful. It's totally useful. If you say it's 7.6% plus or minus 1%, that means it could be as low as 6.6 and could be as high as 8.6. If you have a baseline that you're working off of, like for example, a certain program will kick in when the unemployment rate gets to 5% or lower, you know you're not there yet. Because at lowest, it's 6.6%. So you know you're not at 5. You see what I'm getting at here? Or you could say if it gets to 10, it'll kick in then. Well, at highest, it's 8.6, so it's not there yet. You see what I'm getting at? It still tells you a lot. It doesn't give you infinite precision, but it gives you enough precision to be useful, and that's of 1,000, a sample of 1,000, which is easily gotten. Good stuff. We're on mission 244, Adam. All right, now, what? I want to talk about this, because JC mentioned the word precision earlier, and I want to make sure you guys understand what precision is. I've thrown around a couple terms today. Precision is one. Actually, JC, you threw it out first, and I lobbied it back to you. But there's also the word accuracy versus precision. We are guaranteed 1 immediately. This goes back to Kate's question from earlier about how large a sample. The answer is, as soon as you start sampling, you immediately gain accuracy. But the precision only gets better as you sample more. Now, what part of the wonderful graphs that we saw earlier represent the accuracy of our statistics based on the central limit theorem? Accuracy, accurate. Jamie, say it, go. The bell and the height of the bell, right? We were accurately targeting the average with each bell. Every bell did it. Yes, on average, every bell topped out above mu. Yay, done. But the precision was pretty lame in the beginning. Pretty wide shot, yeah? Pretty wide shot. But as our samples got larger, the precision got better. So the offness, that's why I asked Hattie, how off do you want to be? Earlier, you said 3%. Good, that's a good offness measure. Based on that, I can figure out how big my sample has to be. Fair? Good. Now, this hopefully will help you understand accuracy and precision if that explanation didn't make sense. 4 targets. Assuming that you're shooting, say, a bow and arrow at the targets. You're trying to hit the middle circle in each target. You're trying, that's each of these 4 archers is trying to hit the middle circle in each target. Okay? One of those archers has good accuracy and high precision. One of them has crappy accuracy and crappy precision. One of them has crappy accuracy and high precision. And one of them has good accuracy and low precision. Who wants to take a stab at one of those 4 conditions and tell me which one it is? Anyone you want. Jamie, go. Anyone you want.
Top right.
Top right. Here?
Yeah. Has good precision, low accuracy.
Everybody buy that? Good precision, low accuracy? Why good precision, Jamie?
Because it's a tight. Top in there.
Here's the good precision archers right here. Good precision means not a whole lot of variability. I tried to build this in Excel. I couldn't figure out how to do it. So, good precision, high precision, means not a whole lot of variability between data points. So here's the low precision, clearly. And here's the good precision or the high precision. Good. So if that one is poor accuracy, high precision, who's this? That's the ideal. That's both, yes? That means you're targeting on average and you're hitting very, very close to the average on average. This up here, what could maybe explain this? What could maybe explain this from an archery standpoint or like a gun standpoint?
Closing one eye.
Oh, good! Somehow the scope is off. Whether closing one eye and that's making them move the bow to one side, or say it again.
His weapon isn't zeroed, it's not properly.
Not zeroed. Chances are the archer thinks he or she is looking at the bullseye and they're shooting very well. All you gotta do is fix that scope and they'll hit the bullseye pretty well, I would imagine. Maybe there's a little bit of wind. And the wind's taking a constant wind that's pulling it to one direction, possibly. Something is not being accounted for. Awesome, awesome. So these are obviously the low precision ones, yes? What's this one?
Higher.
Good, that's good accuracy. This one, I would argue, statistically has the same accuracy as this one. Same accuracy. Ernie, Bert. Remember how Ernie's test scores were all clustered around his average, but Bert's were more variable? There's Bert the archer, Ernie the archer. So, they're both targeting the bullseye. So, yeah, we go with this one, of course. So this is neither accuracy nor precision. We can most likely adjust the accuracy by fixing the scope or the wind problem, but the precision would have to be dealt with in some other way. Now, statistically, you deal with precision by getting more of a sample. And you just pick it up automatically. So the central limit theorem guarantees us this, friends. The central limit theorem promises we'll never deal with this situation. Because we automatically start targeting the mu as soon as we start sampling. The only thing is we can move from this to this as we sample more. That's the point. And eventually we get to here. And you know that before you do your study, which is pretty rad, actually. Now, Kate, to finish up, this is your question. And I got no good answer. Textbooks will often tell you you've got to sample at least 30. That's complete and total. It doesn't mean, it's meaningless. It doesn't mean anything. You can do amazing statistics with less than 30, and you can do absolute garbage statistics with more than 30. There's a reason that 30 is used, which we'll get into in 244, I promise you. At least I think there's a reason. I've never seen a historical reason for the number 30, except because we always got told it was 30. I have a pretty good mathematical reason we'll talk about in 244, I promise you then. So the big idea is, even if we accept the number 30, that's pretty small, isn't it? That's pretty small. But you saw that it kicked in almost immediately with 4. Not 30, but 4. That's why I think the 30 is a little superfluous. It's more of a historical anecdote than anything. You can do great statistics with any number of data points you've got. We, in 244 this term, estimated how much oil came out of the BP Deepwater Horizon explosion in 2010, better than the Coast Guard and BP themselves did, with a YouTube video. A YouTube video showing the oil coming out of the pipe. Using some tracking software, a guy in Louisiana helped me with. He tracked some particles in the video. Pretty cool, pretty slick. He found like little pieces of rock or dust or something that got blown by. And you can put this video into the software package. It tracks a piece of particle going by. And it times it. It says it takes it 2 seconds to get from here to here. And then you tell the software, okay, now it takes 2 seconds to get from here to here. How far is there to there in the video? So that gets tricky, because you have to know how big things are in the video. But doing some Googling, we discovered the size of a BP pipe they were using is 14 inches wide. That's how big those pipes were. The one that ruptured was 14 inches wide. So once I knew that, I figured out how big the pipe was in the picture. That's 14 inches. So it went that far, like 28 or 20 inches in however many seconds. Do some conversions on that. You can figure out how fast the oil was coming out of the pipe. Take that, times the cross-sectional area of the pipe, times 86 days, I think it was. I think before they finally shut it down. And you could actually figure out a confidence interval of 95% confident. A confidence interval of at least this much oil, but no more than this much oil, came out of that pipe over 86 days.
How did the people who actually say the numbers that are wrong, how did they even get hired?
I don't know. I thought you were saying, how did they do it? And I was
No,
going to
no,
borrow
no.
Robert's hat and pull a number out of it. Which is essentially what they did. They came out and said, 1,000 barrels a day. I'm watching this video going, 1,000, there's no way. It's like saying I'm 60 feet tall. Or I'm 6 inches tall or something like that. I mean, there's way more than 1,000 barrels a day. So I don't know. It's amazing, it is amazing to me to this day how much statistical misinformation is spread. And as long as you say it with certainty, people will believe you. Listen to any politician. They say things with certainty. What the most amazing is, watch a debate if you can handle this, if you can stomach it on television sometime. Watch a presidential debate or a congressional debate. Then the next day, watch the fact check blogs that pop up, checking what they actually said. It is patently absurd. They're cherry picking things that aren't even related to each other, but they're saying them with such conviction that they seem believable. It's the old adage, if you say it loud enough and often enough, people will believe you. And they will. They will. Drink 8 glasses of water a day, right? You should always drink 8 glasses of water a day. Why? No one has ever shown a reason that that is better than any other number of glasses. You should stay hydrated, yes. But saying you should drink 8 glasses of water a day is like saying the unemployment rate jumped from 7.6 to 7.8%. Here's a good rule of thumb for you. Drink water until your pee is clear.
Yep.
Boom, hydrated. Drink water until your pee is clear. Sorry to be gross, but then you're hydrated. That might take 12 glasses of water. It might take 2. It depends on a lot of stuff in your body. But the problem is that when people say things emphatically with no support behind them, as long as they sound good, they're believed. So that's how they get hired, I guess. That or they just make life hell for everybody else around them and they just get promoted. I don't know. Yeah, JC!
Kind of an answer, I don't know.
Oh, good, go!
But it's like, I was telling you, I took this other class, Speech 240.
Yes.
About how I had to analyze an event that happened and then compare 8 different news outlets to the event itself. So I did, this is off topic, but
No, this is good.
The Benghazi attack, I don't know
Yes.
if many people know what that is, because
It wasn't like
advertised.
the skateboarding dog.
Yeah,
Yes,
so,
exactly.
they're calling it like a spontaneous attack. That's what our news outlets were saying. And I had to compare it to the write-up that, I don't know if it's Congress or whoever did.
The Wire, right.
And they said it was an attack. So they have the word, it is an attack. This is what this event is. But we have all of these statistics and all these other descriptive words that we are using to sway our audience. So that's what I feel like, statistics. We're getting our audience to believe what we want them to.
Exactly. And what's the only way to fix that?
You have to fact check it.
You have to go find the source data yourself.
Hire somebody who actually knows what they're doing.
Or that. But I've given up on that. I say take it into your own hands. Go find the source data yourself. This is why I saw your guys' faces as I was describing the methodology of finding out how much oil. Like when I said, you track the particle in the video. Then you do some research to figure out how big a pp. And I can see your faces going like, oh my God, this is a lot of work. It's a butt ton of work. And it's totally worthwhile if you get a result then that is statistically and numerically believable. It's so much more valuable than some dude in a suit going, yeah, 1,000 barrels a day, we'll have this thing shut down in 3 weeks. No, it's like 5,200 barrels a day and you won't shut it down for 3 months. And the most depressing part about that, just to leave you with another thing to make you feel sick about, even when you add up all the oil that came out of that pipe, worst case, so the highest possible estimate from our estimates, it's still less oil than the United States of America uses in 1 day. It's actually less than 25% of what we use in 1 day. So all that oil that came out is less than 1/4 of what we use in 1 day in this country. That almost made me vomit. Like the BP thing itself almost made me vomit when I did the math. I'm like, this is great math, and I want to cry. But when I found the secondary thing out, I'm like, oh God, now I just want to drink. Yeah, Harrison.
You said like in the beginning of class how you can skew like a looks of data by changing the scales on a graph.
That's what JC's talking about too, yeah.
People they hired, like whoever they hired, they probably did like, hey, this guy looks the best, and he
That's
back it up
quite.
the best.
Oh,
This is
dude.
like the lowest estimate. Cause I got a buddy who works. one of those guys, he tells the oil companies like what they can do to save money. And
Yes, 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 which is very important.
Yep. And he uses statistics a lot.
Of course.
He says, like, that's one of the things you really have to watch when you're trying to like do a business plan for, is you get people who can accurately represent the data in like real time, not for like media outlets and things
Yes.
like that, because it's very hard for the average person to guesstimate how much oil is coming out.
And what is the average person?
Like, well, you know what I mean, like.
I know exactly what you mean. I know exactly what you
You
mean.
never know, and even a lot of like experts, they're not going to take the time to fact check it, so they can do
Oh,
whatever they want.
and you know what's great is Kate said hire someone else to do it for you. Back when I had time to watch television, Stephen Colbert, Jon Stewart, perfect. They will take one story and analyze it for 45 minutes in a humorous, facetious, almost supporting way, and rip it a new one for 45 straight. It's genius.
Yeah,
They are perfect fact checkers. Now they have crews of people doing it for them, obviously, and Colbert's the face on that we laugh with. But that's what you have to do, because if you take it at face value, it's pretty much meaningless and vapid, honestly. JC, what you said, when you suffixed what you said with "if you hadn't heard about that," it just made my heart weep. Because it's like anything else, like what occupies news? It's vapid delivery. When CNN went to 24-hour news, whatever how many decades ago that was, I thought to myself, I'm like, there it goes. It's all over now. Because now they have to fill 24 hours a day with crap.
Yeah.
They can't just do an hour a night, like from 7 to 8, with real news they actually research for 24 hours. Now it's got to just keep... How often do you hear themselves, we got some new data in, why did you report it originally? Why didn't you wait until you had the data to say, we're going to speculate? Stop speculating. Here's my crystal ball. I want to talk about it and not say anything for 25 minutes and command a 6-figure salary. I want that job. Actually, I don't want that job. I'm here with you guys. So anyway, whew, that was a wonderful tangent. But it all bases on this. I mean, this is it. This is the base of all of it. That's the view. That's why it's the bridge over to 244. We'll see it someday, Hattie, I promise. It's the bridge. Not the sumo wrestler bridge, but this is the bridge. I mean, this is what we're going to see. You will see dividing by root n all through 244. And that's where it comes from, is the base in this dual limit theorem. Yeah, Megan's excited now. She's fired up. Yeah. So that's it. That's 243 anyway. Pull the plug on that one. Ha! So we're done. Yay! You guys are fantastic. You worked your tails off in here. I appreciate it. I appreciate it. Hopefully you got something out of it. So we'll see you again on Thursday, I guess, yeah? Got the out of class. Email me if anything happens. If you don't get bell curves, try switching computers. Yes. Oh, okay. So you just got it between 36 and 54. So can I back up here real quick, Skyler? Your 36 is that number, and your 64 is that number. Which means how many standard errors have you gone? How many total have you gone? If you've gone 2 down and 2 up, you've gone 4 total. So this is 4 standard errors. 2 standard errors up and 2 standard errors. 4 total. It's kind of like when you do standard deviation, plus or minus 2 S's. When you go up 2 and down 2, you've gone 4 S's total. That's what you gotta do. And then that is probably the most confusing part of the exam right there. Is just knowing. And then you can reverse engineer this. That's 7. And I forget what that is. 16, so you can solve for sigma. Boom! We'll see you at 2:40.